Morning, everyone. So in the next 40 minutes or so, I'm going to try to explain to you a strategy that's been developing in my mind for how we can collectively pursue a next generation of health and wellness, something that would be economical, more effective, and scalable, so that ultimately the whole planet would be able to enjoy the benefits of the kind of care that we get when people come to the Cleveland Clinic today. The model we have here can't scale to an entire planet, and something transformational is going to have to happen. And it's my view that there's a confluence of things happening both technologically and conceptually that would enable that to happen. My perspective on this goes back, in some sense, 50 years. I started out as a computer person, but with a lot of latent interest in medicine. And then I spent my career in computing, the latter part of it at Microsoft. And while I was doing that, I also became a trustee of the Hutch Cancer Center. I worked as one of Obama's science advisors. And after I retired from Microsoft, I began to devote more and more of my personal energy to understanding the relationship between computing, biology, and medicine as it would evolve in the future. And I became involved with a number of companies in that regard. And each of them is doing interesting work, but when I combined all of them in my mind, I see an opportunity to do something that wouldn't happen naturally from any one of these activities. And I want to explain that to you as we go forward today. Exploring these ideas has led me to ask a few questions over the last few years. And the answers are not completely obvious, but I'm starting to get a pretty strong personal conviction that I know what they are. And the first is, we've got lots of data. We talk about data all the time. There's more and more data. But are we really getting any closer to understanding it? Today, the use of the big data is typically to train models in very narrow areas. And the question is, as we get more and more data, will we be able to make any sense of it? As I've come to understand biology better at a deeper and deeper level and started to look at the molecular aspects of biology, I've kind of come to the conclusion that human biology is actually too complicated for humans. That try as we might, we're never really going to understand it, not in any deep and complete way. And that then leads to the question that says, if understanding that's important, then how about the machines? We're building more and more powerful machines. Will they ultimately come to our rescue, so to speak? Will they be the way in which human biology really becomes understood at a level where we can do something about it? So that led me to think of these 6 things that I'm going to very quickly try to explain to you this morning, such that at the end of this talk, you might go away thinking, wow, there really is a path to something that's completely different. So it begins with looking at what is happening in the evolution of molecular biological assays. We've been doing these more and more. The one that really became prominent, of course, was genomics. And then there's been many more. But there's a new kid on the block there that I think is super important, and I'll briefly explain that. We've watched the computer evolve, from a room-sized machine that was not very powerful 60 years ago to very small computers that are incredibly powerful today. But now we're aggregating those things in order to provide the cloud computing that everybody talks about today. But many of the things that have driven that revolution, the infamous Moore's Law, for example, that talked about the doubling of computer performance because of the doubling of the silicon capabilities, that's sort of running out of gas. And so there's a big shift now where people, the computer architects, are thinking more about specialty architectures. This is not something new. In every generation of computing that I've been involved in, we've always developed some accelerators and then they become an integral part of the way we think about computing in the large sense. And so what's happening now is that we're beginning to design supercomputers, but specifically supercomputers that are going to be focused on this artificial intelligence question. Many people today talk about AI, and for the most part, they really mean ML, machine learning. And when people 40 or 50 years ago originally talked about artificial intelligence, they were really talking about an intelligence. And we sort of usurped that term for a much simpler thing now, which is machine learning. And while it's very valuable, it isn't that real concept of a machine intelligence. But there are several programs in the world now that are focused on it. And the goal now is to build what we call an artificial general intelligence. So we've stuck the general in there and call it AGI, really to distinguish it from the goal of just building fancier and fancier point solutions using deep neural networks and other forms of machine learning. With these increasing capabilities, I believe that we're going to be able to have machines that will learn models of human biology. And this is essentially the way that we're going to come to grips with the fact that the human can't really wrap their head around all the incredible detail that underpins our very existence. If you can get to that, then the next step of medicine, I think, is going to be the pursuit of what we call N of 1, wellness and medicine. And with that, the ability to gain that through largely molecular interventions. You read about CRISPR, Cas9, and other forms of editing the genome. You look at many of the new techniques for inputting changes to our underpinning biology. And yet, we don't really understand completely what we're doing there. And without these improved models, I think it'll be a challenge to shift the practice of medicine to this N of 1 environment. But assuming we can do that, we understand the science, we then will have a new problem, which is how do we regulate that environment? You know, the society depends on some concepts of safety and efficacy through regulation. But that is also historically depended on statistical trials on large numbers of people. And if we're going to personalize medicine to the ultimate degree, that's going to have to change too, and I'll talk a little bit more about that. This concept of machine intelligence has rapidly been accelerating. And you know, if you go back a couple of decades, you saw the emergence of expert systems. These were things where humans actually just coded these applications and tried to reflect their understanding of the problem into the software, which then, you know, integrated and provide some kind of expert advice or operational support. We lived in a bit of an AI winter, if you will, from the days when neural networking first took hold, but then it plateaued in terms of its ability to really perform. And the thing that essentially ended the AI winter was the emergence of two things: really big machines and big data. So, you know, not too many years ago, and even to this day, people talk a lot about big data. That's, you know, the new natural resource, that the answers to many problems lie in that big data. But it turned out the big data and the big machines came largely from the explosive growth of computing and the internet. And it wasn't specifically at the time driven by a lot of new types of data in the biological space. But in this last decade, we've really seen a dramatic increase in our ability to generate that kind of big data too. Once we had these two things, that brought us deep learning, which is really the thing that people are practicing mostly. Things that are just emergent are what we call causal inference, and what's starting to happen, particularly in this quest for artificial general intelligence, is the ability to do what's called transfer learning. Causal inference is really trying to answer the question that makes many people nervous about if the computer builds these models and the models do great things, but we can't explain how they do that. You know, should we worry about that? And so there's a lot of effort through causal inference techniques and others to build models where explication can be performed. Transfer learning is sort of recognizing the difference between humans, where they have so much knowledge. If you want to teach them a new task, you just give them the new task, and at the margin they learn it quickly. They don't need to start over on everything that they learn. The computers today pretty much are one-shot wonders. You train it from nothing to incredible capabilities, but in a very narrow slice. And then when you want to train it even in a related problem, you usually have to go and start over again. And so the idea that machines could also have some transfer learning capability is actively being pursued. And the holy grail at the end of this is the goal of building a superintelligence, a computer that in fact would rival or even exceed the capability of the human intellect. And so let me just show you a little bit about the rate of progress in these things. These are just some pictures in a timeline that goes from left to right. And at the top, you see the evolution of gaming in particular, and then some robotics at the end. On the bottom, you see image generation. Essentially, in the last 6 years, we've gone from something in the gaming realm like playing, Pong, to things where we're able to now have computer-based systems that can play incredibly complicated games at the level of professional players in those games. At the bottom, you can see what it was like in 2013 to start to generate synthetic images of people. And you read about this today in terms of deep fakes for video and images. And you can see why people worry, because in the 4 or 5 years since then, we could generate reasonable static images. You see a moving video, which is essentially one set of human features that is just being continuously computationally morphed. And at the far right, you actually see the current state of the art, where all those faces, including some of them that are people that you might recognize, Meg Whitman, for example, in the middle, all of those are 100% synthetically generated. They weren't started from a photograph. They were basically, completely generated. Dogs, rockets, people. And in a sense, the ability to produce these and do it at high speed results in the ability to create completely synthetic videos. So this trend is going to continue. So last year there was a lot of focus on games. You heard the progress, for example, that the Google DeepMind people made in playing Go. There were really 2 generations of that, and it was important to understand the difference between what happened initially and what happened later, because I think it's an indication of what we have to embrace to solve these problems in the biological domain too. In the beginning, we started trying to train these machines to play Go by training them on the recorded games of all of the best human Go players in the world. And after some period of time, the machine was able to combine the experience of those humans and became a Go player that could beat the world champion Go player, the human player. But then the DeepMind people went away and said, well, what if we didn't actually try to learn from the humans? What if we just told the computers to start from nothing, explore the entire game space, and figure out yourself the best way to play Go? And so 2 machines played each other, for some like 40 days, and they played millions and millions of games. And later, the machine that was trained from its own experience beat the other machine 100 to nothing. A similar thing, went on to happen, and I'll show you in a moment, as the OpenAI people started to train machines to play these professional online esports. But in each of these cases, what we see is when you start and just do these things de novo and harness the power of the machines, you start to be able to do things that exceed what humans had been able to achieve no matter how hard their effort. So for example, Google announced this year in their DeepMind work that they had entered a contest to predict the folding of proteins, which is an incredibly challenging task. And they took a different approach than all the people for the last 20-odd years who've been entering that contest. And their first attempt, they basically exceeded the capabilities of the community substantially, and they became the world champion at that protein folding contest on their first attempt. If you look at this, I'll play the video in just a second. OpenAI is trying to build an artificial general intelligence, and one of their focuses was on gaming. But rather than have a static board game like Go, they decided to see whether the machine could learn to play a multiplayer dynamic video game and to do it at the level of world championship. Now, this game, which I'll play in the background for you, this is actually a recording of a game that was done in April of this year between 5 of these OpenAI bots, because each of them represents an individual player, playing against the world champion human professional team. This is an esports league. You know, the prizes in these annual competitions to the winning teams are in the millions of dollars. So this is a no-nonsense kind of business, and the goal was to see whether or not by training these machines just de novo, not by trying to learn from humans, could they ultimately exceed the capability of the humans? And in April of this year, that happened. 5 of these computers, each a PC running this code, was able to collaborate and beat a team of 5 humans. But the other thing that happened that was not trained for, they then ran an experiment where they just took out one of the humans and put one of the computers in for the human. And interestingly, you know, it had an emergent capability to sit there and play on a human team, even though it had never been trained to do so. And so this is the beginning of what we see happening over and over, which is as the machines become sort of hyperscale, the models start to show emergent behavior. Things that we didn't train them to do, they suddenly demonstrate the capability to do. In this way, you need to think of these things as a bit like, you know, a baby. When the baby's born, you know, it has some brain functions and mental capacity. The autonomic functions are fully functional, but the ability to think and understand, you know, and even control parts of their body, you know, that comes later. And they, at a certain point in time, and in a sense we've seen a pattern over many you know, millions of humans, that we can kind of gauge what the normal, you know, rate of that evolution is. And so the machines are starting to demonstrate a similar thing, but their time cycles are much faster than human learning. So OpenAI this year built a model called GPT-2, which was a language model. And the way that it tries to basically learn and then speak language, or write language, is the model predicts the next word. So you give it a history of words, you give it some word stimulus, and it predicts the next word, and then the next word, and the next word. So they say, that sounds pretty simple. You know, and so the way that they trained it, they said, well, we want this thing to have some general knowledge. So they went out on the web, they took Reddit, you know, which is where people sort of rank web articles, and it has lots of domains of knowledge. And so they went and took all the top-level domains of Reddit. They took all the articles that were voted sort of thumbs up as being interesting. Then they scraped just the text out of those things. That was about 40 gigabytes of data. And they started building these models, bigger and bigger and bigger, always from the same amount of information. And it didn't do anything very interesting at 100 million parameters, 200 million, 500 million, 700 million. A parameter in these models is roughly equal to a synapse in a human brain. And so then suddenly it got to 1.5 billion parameters, and the model started to have emergent capabilities. So remember, there's no system built around this thing. There's no interface other than words. It didn't know what the words meant at the beginning of its life and training. And at 1.5 billion parameters, the thing started to have, we ultimately discovered it had 5 capabilities. It could write whole stories from scratch. It could actually translate language. We discovered at least between English, French, and German. it could be given a text and summarize it. It could do question and answers about things that it had seen in the training cycle, and it demonstrates reading comprehension. So I'm just going to give you sort of a flash look at what it means to do each of these things. So you stimulate it by giving it some words. So on each of these next slides, the plain or white background part is what the input was, and the blue is what the machine wrote back. And so here, we gave it a completely, crazy paragraph to start, and then it starts and it writes a whole story. And the story weaves together things that it learned in the training from Reddit, and it just makes up the rest of it. Now, this turned out to be problematic enough that OpenAI elected to not release this full model because it appeared to be on a path to be a perfect fake news generator. And a big issue is the safety of the emergence of these new AI capabilities. So let me just show you a couple more. Here's translation. Now it learned that largely because it had seen things on the internet, that if you wrote a sentence and an equal sign and another language behind it, and then you gave it another sentence and an equal sign, that it should fill in the equal sign. And so the first sentence, the dog sat on the mat, equals the French of that, and then you write, I'm an American, and it basically produced roughly a French equivalent. Now, what's interesting about this is the system has no memory. It wasn't ever given a corpus of things to learn from that were translations. And the way that it expresses these things is essentially a conceptual expression, not a syntactic or grammatical translation from one language to the next. So in essence, this thing appears to have kind of been like a kid that grows up in a multilingual household. They just think in the union of these languages. So they have conceptual things in their head, and they can say it more than one way. This machine appears to be now doing similar things. Reading comprehension. So here's a whole story about a Supreme Court case and the Chief Justice Roberts and the actions he took. And if you look down at the very bottom, I'm sorry the blue got in the wrong place, there's that little thing you see, TL:(DR). Many of you may know what that is. If you look at a lot of web blogs, people get a little verbose, and people say, that's too long, I didn't read it. So TL:(DR) means too long, didn't read. Now, in the web environment, oftentimes when somebody writes that, some other friendly person will then summarize it for you so that you didn't have to waste your time reading the whole thing. So we put in this story, and we put in TL:(DR), and the model conveniently wrote a 2-sentence summary of the whole story, which was actually quite accurate. Many students, even in certainly grade school and high school, oftentimes will have a tough time doing that kind of summarization in a concise way. It learned open-ended questioning. Now, what's interesting about this is it was not prompted with any new data, a new story like the Chief Justice story. Here, you ask questions, and if the questions ended up containing needed access to the information that was in the corpus that it learned from all the Reddit pages, it coughs up the answer. And so in a sense, it not only took in the text, built the model to predict words, but it ended up in some way that you could say is not completely understood, encoding the knowledge that was in those stories once it learned to read. This is a bit why I think that it didn't really do much until it got to a certain level. And at that level, it had enough capacity, sort of in sort of synaptic senses, to be able to do these things that resemble a lot of what humans do in dealing with languages and words. Then finally, this is the combination of those two things, where we gave it a news story at the margin and then asked it questions about that story. And it's able to extract specific answers from it. One of the things that was interesting there was just an article 2 weeks ago, but this is just someone who was citing it, but The Economist magazine in the UK was creating a writing contest. And so they basically opened this to the public and I think got several thousand submissions. And it was to write a 400-word essay about climate change and what you could do about climate change. And so lots of people submitted these things. But the editors of The Economist decided to do an experiment. They took this model, the GPT-2 model, and they gave it a few stimulating paragraphs or sentences, which was really the challenge for the contest, had it produce several paragraphs of stories, in essence based only on the knowledge that it had from its training, which wasn't specific to climate change in any way. And they put those things together and entered it into the contest blindly. And so there were 6 human judges, and they judged these entrants to decide which ones should be, considered, for further consideration. And you could say, some people said happily, that the humans didn't get skunked by the computer at this point. But 2 judges said, yeah, it's pretty good, go ahead and put it in. The next 2 judges said no, but the reason they said no is they didn't think that the content was very original. And then 2 people just rejected it. So, of course, how could it have any original content? Because it was just, trained on all these web texts. So, these things begin to make you think there's real progression here, and the thing is starting to demonstrate interesting capabilities. Just to show, we took the same model. Instead of training it on text, we trained it on music. And then said, don't predict the next word, predict the next note. Then you could just give it a stimulus of any particular clip of music, and it would immediately generate a new piece of music. So here, they can turn it up a little bit. We gave it 15 seconds of a Chopin concerto, and it immediately produced this composition, which basically sounds like a Chopin concerto. It just isn't one. And so it has all the right voicing, it plays with 10 instruments, and it does this instantaneously. So what is artificial general intelligence? Well, I think it's kind of got several components. It's a computer model, ultimately, that is an expert simultaneously in multiple domains. And importantly, it can reason across those domains. It can combine supervised learning with unsupervised learning and reinforcement learning to master extremely complex systems. It may end up creating a new way to represent knowledge that we can then allow us to reason across in ways that humans can't do on an individual basis. And it may end up creating a capability to explain causation and not just the correlations that you see in some of the models today. Why is it time for this to happen? In part because the computing capability just gets more and more powerful. Here's a graph. You don't have to try to read all the details, but basically it's over the same time period as those images I showed you a few minutes ago, roughly from 2012 or so till the present. And these are the different models and achievements that have been done by the community in that 6 or 7 year period. But the computational capability in that 7-year period to do these kind of problems grew by a factor of 300,000 times. So this is, wildly exceeds what you get out of a Moore's Law phenomenon or anything like that. It's coming because we're building machines that are custom made at super scale to be able to solve these unique kind of problems. And to some extent, we've now concluded that basically training these neural models against these problems can consume all the computing we can aggregate. And so in a sense, the quest for artificial intelligence really becomes a quest to build the world's biggest computers. So let's say we did have a really big computer, bigger than the ones that we have today. And we did the same kind of things we did with words and music. So my idea is, what if I could then say, I don't want to predict the next word, I want to predict the next proteome. The proteome is sort of the new kid on the block in terms of these molecular assays. It's the one that I think has the most to give, and it's been the hardest to crack. And yet it is just starting to emerge where we can do in a single test a substantial fraction, in this case about 25% now today, of all the human proteins in a single test. So if you had that, and perhaps some of the other molecular assays, like the immunome, for example, could you just feed this system molecular assays, extremely pure data, no extraneous features, terrific signal-to-noise ratio, and fed into these big machines, could we in fact train an AGI model to predict, given a history of a protein, of a proteome, let's say for a person, could we then give it an input and have it predict the future proteome of that person? My contention is that if we could do this, that system would essentially have to understand, in some sense, all of human system biology. And if we had that capability, we could probe it to learn about biology. We could use the predictive capability of it in many, many ways. In a sense, it would create an in silico capability to do many of the things that are at the core of biological research, drug development, clinical trials, and ultimately the practice of medicine. And it would then give us an in silico way of exploring completely novel ways to do that. So if we want to move to an N of 1 medicine model, and we want to be able to find these kind of things, how are we going to do it if the humans really don't have that level of understanding? It's essentially like trying to learn Go. You can either kind of learn what the 3,000 years worth of Go players knew, or you can just let the machine go crazy and look for a completely novel way to do it. And so in this talk, I'm advocating that we really start to think about letting go of what we think we know about biology and medicine and come up with a way to use these machines in silico to explore a completely new way to solve these problems. So there's lots of new applications for genomics, and you hear a lot about that. But in reality, the genome is kind of letting us down. And I think with that, you see people pursuing cell-free DNA and mRNA and other things, because in fact, the thing that tells you the whole story of the current state of a human is really best done by the proteome. And it hasn't been around until now. And so as this sort of proteomic capability emerges, I think you're going to see that the relative importance of DNA and these, I'll call these intermediate things like mRNA, they're really all on the way to the end state, which is defined by the proteins in your body. There's 21,000 of them, roughly, and today in these tests we can do about 5,000 of them. Now, one of the things that has been a speculation for quite some time is that these things really contain a lot more information than the other things that we've been dealing with. And the question then is, well, how can you really know? So we actually just did a recent experiment, which Lee Hood, who runs the Institute for System Biology, and Nathan Price, one of his colleagues, allowed me to share here. This is unpublished data. They'll write quite a bit of formal papers about this. But ISB, of which I'm a director, and I was also a member of a group of 108 people about 5 years ago called the Pioneer 100 group. And that group embarked on trying to do as deep a phenotyping study as we could on a time series basis over the course of a year. And ISB spent a huge amount of time analyzing it. Now, 5 years ago, there was no effective way to get any substantial number of proteins included in that deep phenotyping. So we had virtually everything else you could do. We had whole genomes, not just some panels. We had the microbiome, multiple times. We had every kind of blood test imaginable. And they studied this. And then over the last couple years, there started to be some low-scale proteomics available. So they combined a little bit of mass spec work and some other panels that did much smaller samples. And they got 100 to 200 proteins, I forget the exact number, and they added them. And then they went back and said, okay, how many correlations can we find between the health state of these 108 people and all this multi-omic data? And the answer that time was 3,500. In the last few months, my friends at SomaLogic got together with ISB, and we took the 5,000 protein assay, and we took the blood from those 108 people out of the freezer, and we basically did the proteome at 5,000 proteins. We took out the 200 proteins, put in the 5,000 proteins, ran exactly the same analysis. And interestingly, the number of correlations that we had went from 3,500 to 35,000. And I think this is the first quantification of the relative contribution in the big data sense of all the omics we've got, starting with the genome and the metabolome and every other ohm. So even with only a quarter of the proteins represented, we also start to see that these things operate in networks, that even looking at a quarter of them begins to give you some insight because of its linkages into other aspects of the proteome. And the proteome seems to have data about both your past, certainly your present, and it appears to have tremendous predictive power about your future. I became very involved in this. This is a time sequence of plasma proteins. They're from my wife. Unfortunately, 2 years ago, we found she had cancer. And we started to bring to bear in sort of an N-of-1 clinical trial a proteomic history, which we could start because she was also one of those Pioneer 100s. So the top left corner, which is sort of the all blue baseline, everything else is essentially a measurement relative to that baseline, was before she had cancer. And it turns out if you look at the fourth panel, things in her proteome changed dramatically. And while we didn't discover her cancer until 2017, late in 2017, it turns out that if you look at this data, you can see in April of 2016, a year and a half earlier, her proteome started to go crazy. And you can see through the whole course of treatment, that the proteome provides a substantial reflection of all the things that we were trying, chemotherapy and surgery and everything else. And so this was a very personal lesson for me, with some of the world's best people trying to look at this data and understand it. Other than visualizing at this level, which is quite coarse relative to the actual underlying data, it's hard for people in the business today to extract the amount of information that's represented even in that one sequence. So that led me to this question that says, in these high dimensionality problems, should ultimately the humans be guided by the machine? If you read a lot of the popular literature, they all talk about, no, it's the humans that are going to guide the machine to the answer. But in fact, I think it's really quite different, that the machines are going to be the one to guide us to the answers. I want to talk more about this N-of-1 situation and the problems associated with it. This is a clip from a New York Times article from October 9th, I think it was. And it's a story about a drug developed for this girl, Mila, and the drug was named Milacin. And the reason was it was the ultimate ultra-personalized drug. She had essentially a neurodegenerative disease. It had a genetic basis. People had struggled to find for several years what the genetic mutation was because it was in a weird non-coding part of the genome. She went from a healthy kid at age 4 or 5 to basically almost dead by age 9. But in that last year of her life, a guy named Timothy Yu at Boston Children's took on this problem of trying to figure out, A, what was the problem, and B, what could you do about it? Now, it turns out a lot of drug development has been done where we develop oligonucleotide strings. We can sort of produce them in a very reliable way, and then you can load them up into people, and they will complement or make the changes necessary to deal with those, for example, mutations that cause these different diseases. No one had actually ever tried to do it for a specific person, N-of-1 mutation. And they actually worked with the FDA in a remarkable story. And in less than a year, they went from discovering what the missing thing was to designing the oligonucleotide, which took almost no time. Then they went through some process of trying to, prove that it was as safe and efficacious as the other oligonucleotides that were already built exactly the same way but delivered for other generic, more generic illnesses. And then the FDA wrung their hands for a while and ultimately decided that they would allow this drug to be produced, labeled to be used for exactly one person in one trial and nothing else. And that was an incredible breakthrough, because here you had an FDA-approved drug developed in under 1 year for one human, for one disease. And I think that in reality, that is the future of all medicine. Because every person's really different, and we're just kind of dealing with averages now. And the question is, how do you get from where we are to that kind of N of 1 medicine? On the day that New York Times article was published, these two prominent people from the FDA wrote an editorial and published it alongside. And in the editorial, they enumerated many of the challenges that they were struggling with and anticipated struggling with more as we move toward this N of 1 kind of medicine. And so it really leads to a dilemma that with the computing and technology and chemistry that we now command as humans, we can mess around with the basic code of life. We can edit the germline, but we have no idea what we're really doing. We can make a change here and a change there, but it'd be like saying, well, I've never really understood how a whole airplane flew. Let's see if we can optimize it. We'll just start flipping circuit breakers here and there and see if the plane flies any better. And that's kind of what we're doing to people right now. And the question is, how are we going to get past that and then get past it in a way where we could essentially feel comfortable making the decisions to give people these N of 1 capabilities? Here they pointed out, I just cited a few of the things that the FDA folks mentioned. It says, in these N of 1 situations, what evidence is needed before exposing the human to the drug? Even in a rapidly progressing disease, a fatal illness, should the thing that we do precipitate or make the thing worse? Should I take any risk on that? Or is it just better to let them die, and not make it worse? How persuasive should the mechanic or functional data be? How should the dose and regimen be selected? Now, you see, in my mind, as a non-medicine person, all these questions, are clearly derived from a classical way of thinking about drug development and testing. And yet I've just shown you that there's essentially all this new stuff emerging where we could end up with machines that actually, on a person-by-person basis, can understand your system biology. And if I understand that and I can simulate it, then I can answer all these questions, and I don't have to wring my hands about it. So it seems to me that the need for a new model of regulatory science is very clear. That medicine, particularly as it enters this N of 1 world, is going to have to get a lot more like all the other engineering disciplines, that have benefited from computer modeling over the last 20 to 40 years. Today, you couldn't build a building, a bridge, an airplane without essentially trying to model the system as a system. And if you're a test pilot for Boeing these days, you wouldn't think about getting in a brand new, 797 thing and say, well, we slapped it together, we didn't model it, just get in there, fly it, and let us know how it works. Because he can't understand it or she can't understand it, and it's an incredibly complex system. So it's been modeling and simulation that allow us to deal with many of these challenges in all the other engineering fields, and I think we're going to have to adopt that mentality and techniques here. The question is, how do you build the model? And so the ability to learn these models and then explore them at scale through these supercomputing environments, I think, is the ultimate answer. That humans are never going to be able to make an expert system that is an accurate model of a whole human. But I think that the machine can learn that from our own biology. The last part I want to show you is how I think that the idea of in silico discovery and even these types of regulatory problems can also get some help from these evolving artificial general intelligence systems. And so what I'm going to show you is like a 3-minute movie to end this thing that is recently published by OpenAI. It's essentially multi-agent work. ostensibly starting with a quote, simple game of hide and seek. And so listen to this as we finish up here.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment, truly complex and intelligent agents will one day emerge.
So when you add all this together, you realize in this model, this is a little graph that shows the 6 epochs of learning and how many cycles it took and what the relative rewards look like. And you see that the things balance out generation by generation. But to get to this last surf defense thing took about 475 million games. And this is the thing that humans have a tough time understanding. You know, if you say, well, I'm going to sit down and play one of those games and I could play it in a few minutes, and then you multiply a few minutes times 475 million, you realize, well, man, you haven't got a chance in your entire lifetime of playing that many games. And yet, the machines can do this today and are going to be able to do more and more of this. If you say, how many synapses do we have today in the models that are trained for this language, it's about 1.5 times 10 to the 9th. If you look at the estimate of volumetrically determined of the total number of synapses in the average human brain, it's 1.5 times 10 to the 14th. So it turns out we're now within a factor of essentially 10,000 between what we can build today and the equivalent to a human. The difference is humans run at about 30 hertz, and these machines are running about 1 million times faster. And so their ability to explore spaces that would be impossible for any one human or even teams of humans is the way that this kind of learning can happen. So when you think about this was based on a physics model. So just wrap your head around the idea that if we have this model that was trained on molecular data, understands and can predict human system biology, then it's essentially a biological model instead of a physics model. And think of these little hide-and-seek people. They're not hiding and seeking just for a game. The hiders and seekers are basically people, and the tools that we give them are every form of molecular intervention and medical intervention that we know about as we learn. And I just let the thing run. I don't know how long it'll run, but what I can predict is that it'll find, for any given situation, an optimal path. And in fact, this thing they didn't mention, but it turned out they thought that the evolution of these solutions was going to stop earlier. But the thing actually found a bug in the physics model, and it learned how to exploit that. And so it also cautions that, we really want to believe that these models are good, but that the power of this level of exploration is quite incredible. So we have to start and think differently about our role relative to this evolution. In essence, we should think that we're the parents of a polymathic machine prodigy, that it's our baby, and we know it happens to be born with some almost superhuman power, and we've got to raise it right. And if the machines, in fact, learn like children do, they just do it a lot faster. And we understand that we don't know the answers. We only have to help them be prepared to discover the answers. That's a qualitatively different way about thinking about the future of medicine, biology, and human health and wellness. So how do we do a good job as parents? I think this is a super important question. This is just a kind of an interesting thing to close on. This is an article, in Science magazine 2 years ago in July, and I think it had two interesting things when I looked at the quotes here, and I put one in purple. First, it says, a researcher at Carnegie Mellon says, an intriguing possibility is that we're closing the era of comprehensible science. Essentially, research may come to rely on computers not only to do the science, but also to explain it. And then there's another quote. They were asked, well, since you're using these robotic machines to help you do your science, should you make them an author on the papers? And this guy kind of said, well, I wouldn't do that. And then he hedged a little bit and he said, well, when they can read and make sense of the paper, then they can be an author. Well, I just showed you these machines reading and making sense of papers, doing translations, etc. The day is coming soon where both of these things will be possible in machine intelligence. In 1966, Charles Huggins got the Nobel Prize for Medicine and Physiology, and this quote was attributed to him. He said, "Nature can refuse to speak, but she cannot give a wrong answer." My view is that she's waiting for somebody to talk to, but it won't be us unless we get help from an intelligent machine. Thanks a lot.